Hey, welcome back, everybody. So, graphing motion, it's a, there's going to be nothing really major here that you don't understand. If you're taking this physics class, you understand how to do basic graphing and stuff like that. But it is the fundamentals to everything we're going to be doing later in the semester, especially when we get to vectors and we introduce some trigonometry into our motion for analyses. It's going to be highly important, just like what we did in some previous lessons where we were making sure we understood about deriving units and how to step back and really make sure we understand what that means and how to use that to interpret what we're looking at. Graphical analysis is key to pretty much everything in science and very especially here in physics. So with no further ado, let's jump in. Let's take a look at stuff with graphing motion. You'll have a chance to do some practice, and then we'll come back, and then we'll just kind of go from there. Graphing motion. Here we go. Graphing motion, and I want to use some blue ink. I like blue ink. So graphing motion, we're going to take a look at just simple graphical interpretation, analyses, and some very basic calculations before we move on to more complex stuff. So not too challenging, but the basic fundamentals. If anything is in motion, anything is moving, even if we're working with our larger equations in the later units, these fundamentals are literally a part of every single equation that we're going to be looking at. So we just want to make sure that we have a good foundation here. So let's move on to the next thing. What I want you to do is take a moment, and just a second, pause this video, and what I would like you to do is just make a statement about the graph on the left and the graph on the right. Just one or two sentences for each. Probably just one sentence would work, maybe two. It just depends on how you write. Pause the video and give your interpretation for each of these. Go ahead and pause now. All right. So I'm assuming you've unpaused. So this one on the left here, okay? So obviously we can take a look at this and we can see that it's pretty bad. I have a hard time following straight lines. I don't know if you've ever noticed that, but anyway. So if you notice here, initially the position of this thing is here, and then if we come down to here, so obviously, there was a change in its position, which as something is moving, you tend to think, just because this is, y here and this is the x-axis time, change in position, on a horizontal surface, we would think of that as a change in x, okay? So there was a change in x, so the position changed here. And if you, same here, all right, if we follow this, we can also see, we've got an initial position here and an initial position here. So if you think about it, this right here, if all of this right here also represents a change in x, then this would have to be the x initial, this would have to be the x final, right? So that means this is x initial and this is x final, right? And that's how we write it in physics. Sometimes you'll see this like initial is like 1 and final is 2. So you remember back to your basic algebra when you looked at like intercept, your slope intercept and everything, you would say like x2 minus x1, y2 minus y1. It's the same thing, but we tend to use final and initial when we're in physics, simply because we're always going to be looking at a change in position when we're looking at motion, and we always think of initially where was the object when it began, or before it began its motion, and then finally is the final position is where is it at when we're analyzing just that one thing. Okay. All right. So let's I don't know. Let's take a look at the one on the right. So if we think about it, this x-axis here is time. This x-axis right here is also time. So if you look here at this chunk of time compared to this amount of time, there is less time here that this object is in motion. We see that they started from a different initial position, but the amount of distance that is traveled looks about the same. If you look at the lines, the magnitude of the lines are about the same. But even if they weren't, what we can definitely say is right here, this object that's in motion in number 2, it took less time here for it to complete its motion. So we would say that this one here, that the object is traveling faster. Okay. So I'm just making some bullet points. It's traveling faster than the object on the left. Okay. And so by that same token, if we come here, we can say that this one is traveling at a slower rate. So if we call this A and we call this B, now I can say it's traveling at a slower rate than object B. Okay? All right, so that's one thing that we can say. Now, that's where they're different. Where one thing that we can say for sure also is this. So this is your y-axis. It's your x-axis, y-axis, x-axis. Okay? What we can say is, for sure, is understanding a graph that as we go up it's positive, as we go down it's negative. And so if the initial position here, okay, the initial position is right here, and now the initial position, the final position is right here on this one, then that means this thing, that this object was moving in some sort of negative direction, or it was moving with a, we could say, a velocity that is negative. And let's think about this on B as well. Here the initial position is at a more positive value than what this is right here. And so if you think about what you've ever done with like y2 minus y1, x2 minus x1, if we say x final minus x initial, well, here we've got an initial value. Let's just say up here is 10, whatever the unit is. If we say here the final, it's not down there at 0. If we say this final down here is 1, well, 1 minus 10 is negative 9. If we realize that we have a negative value in the calculation, we don't have negative time, we're just counting time. So we could just say however much time that is, right? And so since we know that, velocity equals distance divided by time, if the distance value is going to be negative, then when you divide these two out, you're going to get a negative value. So we can definitively say that the velocity is negative for both of these graphs. And if you think back to what you learned about point and slope, these lines, these are nice straight lines. We have to assume that every single data point is literally connecting those lines. We don't see any data points outside of those lines like on a scatter plot. So what we do is we assume that this is representing an average and that this is at a constant velocity. So we have a constant negative velocity for both of these. Okay. So if you made if your statements had these answers in them, if you had, if you discussed the fact that the one on the right, or which I've labeled B, is traveling at a faster rate than A, and if A is traveling at a slower rate than B, and also that the velocity is showing at a constant rate and negative, give yourself all the points. All right. Let's take a look at something else. Pause this video, and what I want you to do is do the same thing. Pause this video, and I want you to make statements about both of these graphs. Go ahead and pause now. Last time we talked about an initial and a final position, right? And so we just called it x, like xf, xi, x of f, x of I. All right, x sub f, not x of f, sorry, x sub f, x sub I, or just xf, xi. You know, saying sub this all the time is just going to get a little monotonous, and so you'll find that we don't always necessarily do that. All right, so right here, if we look at this one here initially, hang on a second, what I'll do is I'll just sort of make like a little matrix type thing. So initially, and then sort of at the finish, right? So for both of these, I'll kind of make like a little table. Wow, that's a really bad line. That's better. All right. And you know, you can do this however you want. I'm just kind of doing this in a shorthand way for you. So initially right here, if we were to look at the curve of this one compared to this one, this one right here, it makes sense when you're looking at a curve that you're talking about a slope, right? And so if we look at and we did that on the last, well, I just didn't use the word slope directly, but we were looking at the slope of the lines. That's how we were able to figure out whether it was constant or not. Here we see that there's not necessarily constant because we do see a curve on that, right? So here we're not going to say that, hey, we have something moving at a constant rate because we don't have a straight, basically a straight slope line through this. We have a curve through this. And right here, this is a very small slope. And here we see, on this one right here, we see a much larger slope. Okay? Nothing new. This is nothing dazzling for anybody right here, right? And then right here, we say, when this finishes though, so initially, you know, during the very first part of this, you know, we could, during the very first part of this right here, you know, that right there, that's a small slope. And then if you were to come over here and sort of do something similar, let's just say we took the same chunk of time. So I tried to highlight, you know, about the same chunk of time, right? You can see here that there's more of a greater slope in that same amount of time. If we break it up and just look at that part right there, that's a much steeper slope. It's going downward, but it's much steeper as compared to this slope right here. So we say this is a large slope. And so this one right here, this first one here, it has a small slope initially, but then it finishes with a large slope, and this one right here starts with a large slope and it finishes with a small slope. So what does that mean? What in the world does this and this actually mean? All right. Well, you change colors just to help differentiate what's going on. Let's go with purple. I like purple. Yeah, I like purple. All right. So you see a downward slope again. So initial position is here, final position is here. Just like in the previous one, that's going to refer to something with a negative direction, right? And in that so you can see here in that negative direction, here's a small slope, but it ends with a large slope. This slope, the actual slope itself, if you have position, if you look at this, anytime you see, this is basically y over x. And for us, position is y, x is time. So the slope of this line is velocity. So if this thing has a large slope at the end, it has negative direction, and it's speeding up. And the opposite is true. It would have to be true here, except for the fact we know we still have negative direction, right? And since there's a small slope towards the end, then it must be slowing down. And what that means is there's a decrease in velocity in this second one here. I'm sorry. There's a decrease in, well, I'm just going to call it A, or I'll call that one B. I'll call this one A. Could call it 1 and 2. So there's, a slowing down, a decrease in velocity in B, and there's an increase in velocity, speeding up, in A. All right. Okay, here's a little exercise and some basic math for us. Pause this video in just a moment, and what I want you to do is I want you to calculate the acceleration from 0 second to 1 second. Show all of your work, and then we'll do it together and we'll see what you got. Pause the video now. All right, I'm going to assume that you unpaused the video. So let's take a look here. Let's leave it purple. I like purple. I really like purple a lot. Okay, so what we have here, let me put on my glasses. Sometimes I have a harder time seeing what's going on here. All right. Let's see, let me come up with I want a different color. Oh, let's go with purple too. Wow, let's do that. Yeah, let's go with purple. I'm really liking purple. All right, so right here we've got an acceleration from 0 seconds, right? From 0 seconds to 1 second, right? So from here to here. All right, we got 0 seconds to 1 second. So first it's here, and then 1 second later its position is right there. So its position is here, and its position is here. All right, so let's think about what we've got. We know that acceleration equals a change in velocity divided by a change in time. All right, delta V over delta T. So delta means, just like you learn with the whole slope thing, you've got y2 minus y1 over x2 minus x1. So that means we've got velocity final minus velocity initial divided by the final time minus the initial time. All right, the final time, I'm sorry, we'll do the top first. So the final velocity we see here is 40. All right, and you should remember from previous videos, not mention that the unit's right there. So you've got 40 meters per second, right? And the initially it was at that 0 mark. So initially it's 0.0 meters per second. And yes, I know that this is not difficult math. You're thinking, Mr. Tibb, do I have to write all this? And the answer is an emphatic yes. Yes, you do. So, final time. Well, final time is 1 second. Initial time was 0.0 seconds. So essentially, 0 over 0, you can, this is basically 40 meters per second divided by 1 second, and so you should see that you get 40 in meters per second This is 40 meters per second, which is 40 meters per second squared, which meters per second squared, we've already discussed, is the unit of measurement for acceleration. So you should have gotten 40 meters per second, highlighted your points on there. All right, and let's go to the next problem. Pause the video and come up with an answer, show your work for this one. All right, once again, acceleration. So acceleration is delta v over delta t. So we're going to need the final minus the initial divided by the final time minus the initial time. Okay. All right. So we've got a situation here where we're at from 1 second to 4 seconds. So at 1 second into this thing, it is here, and 4 seconds later, it is here. All right, and so the final velocity right here, right? So we know that this is this final position. There's the final velocity, initial velocity. All right, and so final velocity we can see is 100 meters per second. We see initially it was at the 40 meters per second. So this is the same object moving. It's just moving at different rates at different times of its travel, and this graph is representing that. Okay, so think about if you're moving, you're not always moving at the same speed, at the same rate. I always should say velocity, because velocity, remember, is a vector, so you're moving in a particular direction. So you're moving, you're moving at a certain rate, but you're not always moving at the same rate. You're speeding up, you're slowing down. You're speeding up, you're slowing down, and you're changing direction. And so graphs are going to represent that. Okay. All right. So now you should see that the final time was at the 4 second mark, and the initial time was at the 1 second mark. All right. So, 100 minus 40, what does that give us? 60 meters per second, and we can subtract those because they're like units. And then 4 minus 1 is 3. You can see there's absolutely nothing rocket science about this math. And 60 divided by 3, punch that into a calculator if you need to, but you should get 20, and that's meters per second, and so that's 20 meters per second squared. And right now we're not really worrying too much about that, the whole sig fig and stuff like that. It's just coming out to a nice even number, 20 meters per second. So I mean, technically the best way to write this would be 20.0 meters per second squared. So yes, we will be, all your final answers are going to have to be reported in correct sig figs, etc., all that good stuff. Everything you learned in chemistry and all that other stuff, yes, we're going to have to do that. We're just looking at the basics right now. Okay. Let's try another one. Pause the video, answer this question. All right, acceleration again for this one. Acceleration delta v over delta t, same thing. Final velocity minus the initial velocity, the final time minus the initial time. And yeah, so when you write your lowercase t's, write them like this, otherwise it looks like you're writing a plus symbol, which is why you should be doing it that way. Okay. All right. So we're going from 4 seconds. So we're going from the 4 second mark down to 12 seconds. So 12 seconds brings us all the way down here, right? That mark right there. That's what we're doing right here. So the final velocity, right? If you look at this thing, the final velocity would be down here, and if you come all the way across, you can see that that is a negative 60 meters per second minus our initial. Well, initially we were up here at 100 meters per second. And the final time, what is that? The final time is at 12 seconds. And the initial time, that's up there at so 4 seconds into the trip, right? And so negative 60 minus 100 gives you negative 160 meters per second. 12 minus 4 is 8 seconds, right? So 160 divided by 8, that's going to give you a negative 160 divided by 8. It's going to give you a negative, what, 20? And then that would be meters per second, which is a negative 20 meters per second squared. And that makes sense considering that the slope of this line is a negative slope. We should have a negative magnitude. All right. Everything should match up. So here's the very basics of your signs are important, and then listing out your variables and getting those correct. That's highly important. All right. Let's take a look at one more. Pause the video. And what I'd like you to do is this. I want you to imagine someone's on a roof. They've got a cat. And that cat is launched off the roof into the swimming pool below. It's water, so the cat's not going to get hurt. This is just a problem I saw in a book, and I thought it was kind of cute. I thought I'd share it with you. Upon entering the pool, the cat encounters a 50 Newton upward resistance force. And we're going to assume that force is constant. So in these first couple units, we're always assuming something about something being constant. We will look at something not being constant in later units. But right now we assume constant. And our slope lines are going to mostly reflect that. Which one of the velocity time graphs that's above represents the motion of the cat? Pick one of those and give a supporting answer as to why. Pause the video and do that now. All right. Okay, let's think about this. You've got a cat. All right, there's the roof of the house. Well, that's a really ugly roof. Cat, let's just say this represents the cat. The cat is, according to this thing right here, approximately 50 kilogram cat. That's the mass of the cat off the roof and swimming pool. And so this cat is going to accelerate downward. And then there's a swimming pool down here, bunch of water, and the cat's going to hit this right here, and this problem says that there is an upward force of 50 newtons. The cat's weight is also 50 newtons, and this thing is accelerating downward. Okay. So another way to say that is that we have a negative acceleration. Okay, we usually write negative acceleration. So if you want, so I don't confuse you, let me go ahead and just do that. I'm going to put a negative acceleration, which means an acceleration downward, right? So then it hits the water. If it's accelerating downward with 50 newtons of force, and the water, when it hits it, is exerting 50 newtons of force, then that means we have balanced forces. If there's balanced forces, that means when the cat hits the water, that cat stops for it literally just stops. It doesn't bounce. It just stops. So now let's think about this. If this cat is accelerating downward, then it's going to exhibit a negative velocity. All right, well, right here, this is a negative velocity. And when the cat hits here, when it hits that, when it comes to this point where whatever it encounters, now it moves in this direction. This implies right here that there would have to be a force greater than 50 newtons. That's what this would have to apply. That'd be the only way that when it hits right here that it would move upward in this direction. So we know this can't be it. So you should have seen that B is the correct answer. All right. If we look at this right here, 50 newtons, so there's a negative velocity. Well, here's a negative velocity, so we can see here the velocity for C starts out right here at a constant. Over this period of time, it is a constant velocity. It's not doing anything. It's moving at basically a constant rate. It's doing really nothing. And then all of a sudden the velocity increases. This is moving upward. So this right here assumes a positive velocity, which would then yield a positive acceleration. So this one cannot be it. Okay, because remember, acceleration is delta v over delta t. If we have a positive, if the velocity is positive, then once we do the math here, we're going to get a positive acceleration in our equation. So this one, this has to be it. So right here, the cat is falling down at 50 newtons. Bam! At that point right there, it strikes the water. And then right there, it strikes the water, and that's where the balance force is of 50 newtons. So there's 50 newtons downward, 50 newtons upward, and then if it's an equal force, then it's not moving back up and it's not moving further into the water. And so for a period of time, it's just sitting there, not moving, zero velocity. So if you said B, give yourself a point. And that's the basics. Keep in mind that you're going to want to look for, find your initial position, that your xi, your final position, your xf, and you need to know your initial and final times as well. And then from there, you're just kind of using some rationale. Is the motion, is it exhibiting a positive or a negative value based on the situation? All right. This should have helped put some of this in perspective for you. Go back, take a look. We've looked at how to just do some basic calculations where we have a negative acceleration. Here we continue seeing positive acceleration because we saw a positive slope. There was still a positive slope there, just at a different rate. It was a steeper slope. You should see that this slope here is steeper than that slope, which makes sense. As a matter of fact, how steep? Twice as steep, right? And then here we were beginning to sort of qualitatively interpret what our values would be just by the basics there. And the same here. All right, and then learning how to assign variables to the graph. We didn't need numbers, we just needed the concept of variables to be able to do that. All right? All right, good luck. And there you go. Graphing motion. Pretty simple task. It's all about looking at the slope. It's all about looking at what's going on with basically your function. All right, so understanding what the function of the slope is helps you really to understand what's going on, particularly with our motion. Right, we saw that in the lesson. So make sure you work on the practice problems. As always, the answers are going to be posted for you. The solutions are there, and then we will use this to move forward into the next thing. You'll be actually doing your own motion where you'll be using some fairly, it's decently high-tech equipment, and we'll be doing some live graphical motion and analyses. It's kind of fun. I'll see you on the next lesson. It's always good to see you. Take care. Good luck. Bye.